Okay, welcome to chapter 21. Section 2 and section 3 I'm going to cover together. This topic is going to be called molar specific heat of an ideal gas and equipartition of energy. So we're going to define something known as specific heat at constant volume and specific heat at constant pressure, and then we're going to see what the differences of those are. Right? So the theory starts with the concept of specific heat. When we were in solids and liquids, we saw this equation, Q is equal to mc delta T. And remember we said Q is the amount of heat flowing into a liquid or solid, M is the mass of the solid, and C is the specific heat of the solid, right? For solids and liquids, the specific heat can be defined as Q over the mass times the change in temperature. So notice for solids and liquids, we define the specific heat per unit mass, right? For gases, we define it per moles. So for gases, it's going to be C is defined as dQ over N dt, right? Okay, so this one is going to be called the molar specific heat. So instead of dividing it by mass, we're dividing it by the number of moles. Okay, then we can subdivide this into two categories. We have the specific heat at constant volume and the specific heat at constant pressure. So we can write it this way: the specific heat dQ over N dt while holding the volume of the gas constant, right? Or this will be called the specific heat at constant volume, and then the specific heat at constant pressure, dQ dt, dQ over N dt at constant pressure while holding the pressure constant, right? So then we can calculate what the molar specific heat at constant volume is for a gas, and then we can calculate what the molar specific heat at constant pressure is, right? Okay, so then the constant volume, the PV diagram for constant volume will look like something like this. So you say, let's say the initial volume of the gas is like this. So we are pouring in heat into a gas while keeping the volume constant. So the only thing that is changing is the pressure, right? So the heat is coming into the gas, right? And then the pressure of the gas is increasing, right? So then what will the molar specific heat be? Well, so at constant volume, what is the work done by the gas? Zero, right? So the gas does no work. So we can say here Q into gas is equal to change in internal energy of the gas, right? Well, if the gas is a monatomic gas, right, we already mentioned that it has 3 degrees of freedom. So the change in internal energy is going to equal what? 3 halves nR dt, right? So then if we write this as dt can come down here, right? You notice that this is beginning to look a lot like this. So we have here Q into gas, right? Divided by dt is equal to 3 halves nR. And of course we can also bring the n down here, right? Then bring the n down here, and then this one will equal what? 3 halves R. Well, the molar specific heat of an ideal gas, a monatomic ideal gas, will therefore equal 3 halves R, right? Now, in the case where the specific heat at constant volume is constant, right, what's going to happen? dQ is going to equal NCV dt, right? So this is, in actuality, it's a derivative equation. dQ is equal to NCV dt. Then we can integrate this, right? For gases whose molar specific heat doesn't depend on the temperature, right? Then the N and the CV can come out of the integral, right? So then we have here Q is equal to NCV integral dt, and then Q is equal to NCV delta T, right? Because we're assuming CV is constant. Then we can set this equal to this, right? We can say Q over N delta T is equal to CV. And then here we have Q into gas divided by N delta T is 3 halves R. Therefore, the molar specific heat of an ideal gas CV is equal to 3 halves R. CV is equal to 3 halves R, right? And then remember R was equal to 8.31. Right, so if we do 3 halves times 8.31, we're going to get what? So if we write down the specific heat of some monatomic gases, these are the values that we see. CV of neon, CV of helium, CV of argon, CV of krypton. This is 12.7, 12.5, 12.5, this is 12.3, right? So you could notice there is a little bit of a deviation. The 12.5 matches the 12.47 very closely. So this is exactly equal to that, it's just rounded. Then you can see the neon is a little bit higher and then the krypton is a little bit lower. So in order to fully understand the little deviations, we need a fuller explanation with quantum physics and the developments of modern physics, right? So the classical physics theory will not be able to explain completely all those little deviations, right? What the molar specific heat at constant pressure will be, okay? So we have the pressure, constant pressure will look something like this, right? PV, then it will start here at V1, and then the pressure will be constant. So if we pour in heat into the gas, right, the gas will expand. We can keep it an isobaric process, right? Keep the pressure constant. So the pressure can stay at a certain P1, right? So what's that going to equal? Q into gas is equal to change in internal energy of gas plus the work done by the gas. Right? So we have here Q into gas equals 3/2 nR delta T plus, and then the work done by the gas is going to equal the pressure of the gas times the change in volume. And remember, the pressure of the gas is staying constant, right? And remember, only the volume is changing, the pressure is not changing, so the pressure is staying constant. P delta V is equal to nR delta T, right? Then I can substitute that into there. We have 3/2 nR delta T plus, and then P delta V is going to equal nR delta T. Then we can add those, then we have Q into gas is equal to 5/2 nR delta T, right? Then we can do the same thing that we did before. Then remember the definition of Cp was equal to 1 over n dq dt, right? And then we can do same thing. We can say dq is equal to ncp dt. This is while holding the pressure constant, right? And then we can integrate that, and we have q is equal to ncp delta t. Then I can equate that to this. So I can say, in the cases where the specific heat at constant pressure is constant, then I can pull that out, and then this will just be delta T, and then this will be Q. Then I can equate that to this. I can say NCP delta T, Cp is equal to Cv plus R, right? Why? Because Cv was equal to 3/2 R, and then if you add R to that, you get 5/2 R, right? And then that's equal to Cp, okay? So Cp is always a little bit more, okay? Let's try to understand why that is the case. Okay, so remember how Cp was defined. Cp was defined as 1 over n dq dt, right? Cv was defined as 1 over n dq dt. And then we're seeing that Cp is larger than Cv. Why is that? Well, because in the case of constant pressure, we have here the Q into gas equals work done by the gas plus change in internal energy of the gas. In constant volume, we have Q into gas is equal to change in internal energy of the gas. For constant volume, the gas does no work. So if we pour a certain amount of heat into the gas at constant volume, right, all of the heat that we put in goes into changing its internal energy, right? So the gas heats up more. In the case of constant pressure, the heat that we put in, some of it goes into changing its internal energy, some of it goes into the gas doing work. We're allowing the gas to expand and do work, right? So the temperature change of the gas in constant pressure is not as much, right? So since the temperature change is not as much, so for a certain amount of heat flow, the delta T is less, right? That means the Cp is more, okay? For a given amount of heat flow for constant volume, the change in temperature is more, and therefore the CV is less, right? So that means a gas is easier to heat up at constant volume because all the heat that you put in goes into changing its temperature. What are the units of CV and CP? Let's talk a little bit about the units. CV is equal to 1 over N dQ dt, right? So this is going to be joules per mole, and then dt can be Celsius or Kelvin, it doesn't matter. So we can put it as Celsius. Joules per mole Celsius, right? Except for there was a couple of them that were a little bit of exceptions, 12.3 or 12.7. But as defaults, we'll use this as the results, 12.5 and then 20.8, right? So now let's talk about the equipartition of energy. What does that mean? Well, what happens if the molecule is a diatomic or a triatomic, right? If the molecule is diatomic, okay, well, how many degrees of freedom do you add? So now we see that, imagine you have two objects that are connected by a thin rod. How many degrees of freedom are you adding? Well, the whole thing can move in the x direction. So let's assume this is the x and y. So it can translate in the x direction, so that's 1 degree of freedom. It can translate in the y direction, that's a second degree of freedom, right? Then you have the z direction. It can come out of the board and into the board, that's the 3rd degree of freedom, right? Then it can rotate this way, right? This way like this, about the y-axis. So this is a topic that we talk about in physics 1, right? Rotational kinetic energy. And then I is called the moment of inertia about the y-axis, IYY, right? So then the particle, the two diatomic molecule would have to rotate this way, like this, about the y-axis in order for this kinetic energy to apply, right? So that adds 1 more degree of freedom, 1 more degree of freedom. Okay, it could also rotate about the z-axis this way, right? Like that. So it can go like this way like this, right? And then about the y-axis was like that. You see? So then the kinetic energy in the z direction, 1/2 IZZ omega squared, and then the IZZ is the moment of inertia of the object about the z-axis. The z-axis is the axis coming out of the board. And then so this adds 1 more degree of freedom, 1 more degree of freedom. Okay? Then there's the kinetic energy in the around the x-axis like this, right? It can go like that. Okay? Kinetic energy about the x-axis, 1/2 I xx omega squared, right? But what we're going to see is that the moment of inertia about the x-axis is negligible compared to the kinetic energy about the y and the z-axis, right? This one is much more negligible. Why? Because the moment of inertia about the x-axis, Ixx, is much, much smaller than the Iyy and the Izz, right? Iyy and the Izz are comparable to each other. Why is the Ixx so much smaller? Because all the object is more closely distributed to the x-axis. They're much closer. Whereas about the y-axis, the distance is this, you see? Like this, from the center to each object. And for the z-axis, which is this one, right, the distance is also this, right, from here to here and from here to here, right? So the distance of each particle from the origin is much further away than its distance from the x-axis, this one right here. So the moment of inertia about the x-axis, much, much negligible. That means the kinetic energy is much negligible in the x direction compared to the y and the z, right? So you're really adding 2 more degrees of freedom, right? So RT, right? So then that's the total energy, of the gas, right? Right now we are assuming that the gas doesn't have any potential energy yet, right? It only has kinetic energy, right? And then the N cancels, and then the delta T cancels, and the delta T cancels, right? It's actually equal to the same CP as for a monatomic gas, right? Remember the CP for a monatomic gas was 5/2 R. So the CV for a monatomic gas is 5/2 R now. So then what will the CP be? Okay, so the CP will just equal CV plus R. So it's going to equal 5/2 R plus R. So it's going to equal 7/2 R, right? So then you add another 8.31 to that. So now everything went up at constant pressure. This and this, the Cp is always larger than the Cv, right? So they both went up, and that means because it has different kinds of motion, the change in temperature is less for a given amount of heat flow, okay? Now, at higher temperatures, we're gonna add 2 more degrees of freedom, okay? At higher temperatures, okay? So what can happen? At higher temperatures, the object can act like almost like a spring, right? And then it can vibrate this way. It can go in and out, right? Because it's so hot, therefore its motion of vibration of the molecules is increasing. So how many degrees of freedom are we adding? So we're adding 1/2 mv squared this motion, right? It's almost like a block and a spring problem. We're going to add the degree of freedom having to do with the kinetic energy of vibration, right? So this is the kinetic energy of vibration, right? And then we're going to add a degree of freedom having to do with almost like the potential energy of a spring block system, right? Remember in physics 1, the potential energy of a spring and a block is equal to 1/2 kx squared, where k was the spring constant of the spring, right? So then we're going to add that internal mutual potential energy of the system. So that's a potential energy of the molecules, we can say, of molecules, or we can call it molecular bonding. Right? So we're adding the kinetic energy of the vibration of the molecules and the potential energy molecular bonding. So this will occur at higher temperatures. So this is why we call this equipartition of energy. Every time something new is happening, when we made the molecule diatomic gas, we added 2 degrees of freedom. Then when we increased the temperature, we added 2 more degrees of freedom, right? So then what's going to happen? The total energy of this, and then you get 9/2 R. Okay. Now for polyatomic gases, let's say H2O, how many degrees of freedom will they have? Well, they'll have the motion in the x direction, motion in the y direction, right? Motion in the z direction, and then how many different kinds of rotations? Well, for them, all 3 rotations are available. They can rotate this way about the x-axis, right? They can rotate this way like this, they can rotate this way, and then they can rotate this way. Around the y-axis, around the x-axis, and around the z-axis. So neither of the rotations is negligible compared to the other one. Whereas a diatomic gas, the x-axis was negligible compared to the other 2, right? To these ones. So then you have here kinetic energy in the x, 1/2 Ixx omega squared. Kinetic energy in the y, 1/2 Iyy omega squared. And then the kinetic energy in the z, 1/2 Izz omega squared. If the gas has only 6 degrees of freedom, then the total energy is going to be 6, and then each one is going to give you 1/2 nRT, right? So it's going to be 3 nRT, and then the Cv for that gas is going to equal 3R, right? And then the Cp is going to equal Cv plus R, so then it's going to equal 4R, right? So if you do the number with this, Cv ends up becoming 3 times 8.31, so that's going to be 24.9, right? And then the Cp is going to be 4 times 8.31, it's going to be 33.24, okay? Now if we look at the numbers for this, the real results for water, it ends up that for water, the Cv is equal to 27.0 for water, 27.0, then this is at a temperature of 300 Kelvin, and then the Cp is equal to 35.4. Okay, and then for carbon dioxide, the Cv is 28.5, right? Cv is 28.5, and then the Cp is equal to 37.0, right? So you can see here that there's quite a bit of departure from the simplistic view that we are taking here, the 6 degrees of freedom, 24.9. This is larger than that, and then the Cp this one is also larger than that. So the 27.0 is slightly larger than that, and then the 28.5 is even more larger than that. So you could perhaps explain this by introducing another degree of freedom, right? Because the molecules are triatomic, they're vibrating like this. Even at low temperatures, even if it's not very high temperature, the vibrational mode of energy is probably producing another degree of freedom, right? So if you add one more degree of freedom, then you're going to end up having 7 halves nR, T, right? And then if you add that degree of freedom, CV is equal to 7 halves R, and CP is equal to 9 halves R. So if you explain it that way, are we closer now? If you do 3.5 times 8.31, that's going to be 29.1. Okay, then that is close to the carbon dioxide, slightly higher, and it's not really that close to water. So that explanation by itself would not suffice. So some more quantum physics explanations we'll have to do, right? By just introducing that extra degree of freedom, we are not able to explain all the deviations from that, okay? So now you can see how classical physics can explain, at least to some degree, how to calculate what the CV value is and what the CP values are for different kinds of gases, whether they be monatomic, diatomic, and polyatomic, okay? Thank you very much.